Hi, I'm Hadley McIntosh-Marchek from the American Chemical Society. Welcome to this media briefing for ACS Fall 2021. We're joined today by Dr. Tom Runčevski from Southern Methodist University. He's using Titan in a glass experiments to explore the mineral makeup of one of Saturn's moons. Dr. Runčevski?
Hello, thank you very much for the invitation and having me here. So first, I want to very briefly mention why we are interested in Titan, and then follow up with our newest results on the mineralogy of Titan. Well, the reason why we are so interested in Titan is because, simply put, Titan is a very interesting world. It is Saturn's moon, largest Saturn's moon, and it is the only place in the solar system, besides Earth, that has a substantial atmosphere. Now, that atmosphere is predominantly made of nitrogen and methane, not 95% nitrogen and 5% methane. So nitrogen and methane, fueled by energy from the sun, from Saturn's magnetosphere, and also from a couple of processes on the surface of Titan, they react one with another, and they create a vast library of organic molecules. So we can find benzene, we can find ethane, ethylene, acetonitrile, propionitrile, and many other molecules that the Cassini-Huygens mission detected, and that's how we know that they exist in Titan. Now, all of these molecules that are synthesized in the upper atmosphere, they will descend, and as they descend, the temperature of the atmosphere is decreasing, so they will start condensing. The first part in which they will condense is the haze of Titan. That is very characteristic, and whenever we see a picture of Titan, we can see that haze that is quite familiar for Titan. But then once they go on the surface, they descend and they precipitate, of course, carried by methane rainfall, and then they make the surface of Titan. Now, the surface of Titan is extremely interesting. The temperature is pretty constant, around 93 Kelvin. The pressure is very close to Earth, 1.45 atmospheres. Under these conditions, only methane, ethane, and propane would be gas or liquid. Any other organic compound would be solid. So think about, for example, benzene. If benzene has been synthesized in the atmosphere and descends to the surface of Titan, then benzene will be solid. If benzene is solid and naturally produced, benzene is in fact a mineral on Titan. If it's a chemical for us, laboratory chemical, for Titan it's a mineral. And Titan is extremely rich in this in its mineralogical makeup. Moreover, Titan has huge lakes, or better say seas, made of ethane. And around those seas, we have deposits of a lot of organics that have been first dissolved in the seas, carried by the methane rainfall. And as the seas are evaporating, we know that they evaporate in cyclic process, very similar to Earth. And they will make up the mineral deposits of Titan. Now, this is extremely interesting. And for us, our goal is to mimic the conditions that occur in Titan and learn a little bit more about the chemical, but also structural composition of this mineralogical makeup. Now, it is very simple to say benzene will, or acetonitrile, propionitrile will dissolve in the lake and precipitate in form of mineral. It is simple to say, but it's not as simple to study because, as we know, as solid-state organic chemists, molecules in their solid state, they can exist as molecular crystals, but it can also form hydrates, clatrates, co-crystals. So there is, and the co-crystals can be in a very different stoichiometry, 1 to 1, 1 to 3, and so on. So Titan does feature all of these types of solid state formulations from organical standpoint. Together with colleagues from GPL NASA and ANSTO, recently published a really interesting Council of Chemical Research paper, and if someone is interested to see the status of the field so far, I kindly recommend to see that paper. That I guess it will be in this current issue of Council of Chemical Research. But in that article, actually, we say that it's unknown, and a lot of research is welcomed in this field. In this presentation, or in the presentation that I will give at the ACS meeting, I will focus only on two chemicals, acetonitrile and propionitrile, and I will try to answer some of these questions about those two molecules. Now, what we are interested about those two and why we chose exactly those two. Acetylnitrile is detected to exist in Titan. It's detected by Hasidic equations, and it's also by a lot of theoretical modeling. What is interesting is that if we follow the production pathways starting from nitrogen and methane to acetylnitrile and to propionitrile, they follow the same reaction pathways. So our logic is, if we have acetylnitrile being synthesized at some point in Titan, some point in space and in time, we'll have propionitrile as well. And it is very simplistic to study solely only propionitrile, only acetylnitrile, how they will behave, because as organic chemists, we know that mixtures they have completely different behavior as compared to pure solids, pure compounds. And that's what we did. In this work, we took a look on acetylnitrile and propionitrile as a mixture, how they will behave when they are mixed and how they will behave when they're alone. What we discovered is quite interesting. First of all, when we have pure acetylnitrile, let's say, the freezing point is being reduced for as much as 60 Kelvin from the freezing of acetylnitrile to the freezing of the eutectic point of mixture of acetylnitrile and propionitrile. Now, why is this important and how it can inform the studies of Titan? As I said, as these molecules are descending to the surface, the temperature of Titan is decreasing, and they will start condensing in aerosols and building up the haze. 60 Kelvin in difference may translate to hundreds of kilometers different altitude at which we can see crystallization of acetylnitrile if it's together with propionitrile or if it's alone. This is one of the applications of this type of physical chemistry, organic physical chemistry research translated to planetary science research. Another part of our research that was quite unknown was the structure of propionitrile. When we started working on this, that was 2 years ago, it was incredibly surprising to us to learn that the crystal structure of propionitrile is unknown. Propionitrile is one of the most used solvents on Earth. I'm 100% sure that 99% of all of the audience at the ACS meeting will have propionitrile in their lab. The fact that we don't know the crystal structure is ridiculous, and we decided to go after. Interestingly, the structure was published within a couple of months after we sold it, but that did not stop us to perform a very comprehensive research on propionitrile. In fact, we solved 2 more structures of propionitrile that are obtained upon heating and upon cooling of the stable form of propionitrile. Why am I bringing this up? I'm bringing this up because what we discovered is that if propionitrile is alone, that is without a mixture with acetylnitrile, it will crystallize in its thermodynamically stable orthorhombic form. However, if it's mixed with acetylnitrile, we have a completely different kinetically trapped crystallization of the monoclinic phase. And it's quite interesting because this kind of phase trapping, we see it on minerals on Earth. And in this case, we see it also on Titan. And it is very interesting to consider it when we model, for example, the spectral features of the aerosols in the haze or the spectral features of the surface and so on. So it's quite interesting to consider how the existence of mixtures can guide the crystallization of certain polymers. Finally, we applied a couple of new techniques, new in the sense of the research on Titan, such as quasi-elastic neutron scattering that is giving us information also on the dynamics. What we learned is that this type of molecules, acetylnitrile, propionitrile, because they are not in their crystal structure, they are not connected by strong bonds, hydrogen bonding or such. They're bonded by loose van der Waals forces. Because of that, there is a pronounced dynamic in their crystal structure. So we see rotations of metal group that are perpetually rotating. That's quite interesting because in the future, we might connect and correlate those movements with potentially transfer of energy or potentially explaining some of the properties of the structure. And finally, we also discovered that some of these polymorphs are polar, which is quite interesting because polarity plays an incredibly important role in the origins of life. So you can imagine how important it would be to have, for example, propionitrile being templated with a polar surface. And that polar surface in the future can serve as a template for other molecules, and it may help in modeling prebiotic chemistry on Earth or potentially life on Titan.
Thanks, Dr. Runčevski. I'd like to just ask you a few questions about your work. To start with, what got you interested in studying Titan?
So thank you very much for the question. Titan is very interesting world, as I said, for the fact that it has atmosphere very much like Earth. It's so much different in some aspects from Earth. But the reason why I personally got involved in Titan is the fact that I do believe that organic physical chemistry plays a very crucial role in this type of research. Namely, planetary research mostly has been focused on inorganic solid state structures, because, for example, our moon or Mars are made of inorganics, or planetary research has also been focused quite much on atmospheric chemistry and chemistry in gas. However, Titan does demand a completely new approach. Titan is one organic chemical laboratory, pretty much on a planetary scale. And I do believe that solid state organic chemistry or physical organic chemistry is pretty much the right field of chemistry to help understand this moon a little bit better. And that is exactly what we do in my lab.
Great. So as you said, Titan is Saturn's largest moon. How is it similar to Earth, and what are some of its differences?
Right. So the first similarity to Earth is the fact that Titan and Earth are only two places in our solar system that have substantial atmosphere. Now, another similarity is that we do have the same cycle of mass in Earth and on Titan. However, there are a lot of differences. For example, on Earth, we have water. On Titan, the same role of water is played by methane. So we have evaporating and condensation of methane. We have methane storms. We have thunders, and they are filling the lakes and seas of Titan. Then those lakes and seas would evaporate, and then we have that cycling. That is pretty much similar to Earth. In fact, it's very similar to early Earth, prebiotic Earth. And that is one of the reasons why NASA and pretty much everyone is interested in Titan, because it could theoretically foster life. Of course, not our life, the way that we have it on Earth, but a sort of methanogenic life. There are also another similarities yet differences with Earth. For example, we see karstic landscapes on Titan, pretty much similar to the ones that we have on Earth. We see a lot of features on Titan that are similar to young Earth. On the side of differences, the temperature is different, not that different, 93 Kelvin versus our temperature. There's not that much of a difference, but still there are. On the similarity side, we have the pressure being pretty similar on Earth. So all in all, it is, of course, very interesting place to be.
Yeah. So what can scientists learn then about the origins of life by studying Titan?
Well, whenever someone asks or someone tries to answer a question about the origins of life, there's always a big controversy. So in my opinion, for now, we cannot answer that question because there's so much to be learned about the basics of what can lead to life, what is there on Titan, what was there on Earth when life started. So in my opinion, for now, we should more focus on understanding how that world looks like in the future to be able to connect it with origins of life. But of course, the origins of life is one of our biggest motivation why we study Titan in the first place.
Awesome. So in your experiments, you replicated Titan's conditions in small glass cylinders. What did you do to recreate the weather and atmospheric conditions that are actually found on Titan? And who are some of your collaborators in recreating these experiments?
Right. So when we said mimicking Titan in glass cylinders, that's very simplistic. It is incredibly difficult to mimic Titan because, as I said, first of all, we don't really know how many chemicals are there But we do know that we should and we have to start from somewhere. So what we do is we start with the basics. We say, okay, we have A, B, and C, and D. Let's first try to study pure. Let's then mix them together in the binary mixtures, then mix them in the ternary mixtures, and so on. So the closest that we can do currently on Earth to mimic this, this type of environment would be the following. We do know that the surface of Titan, the ground surface, I mean, is made of ice, water ice. So we can take a glass cylinder or diffraction capillary and put water, freeze it to 93 Kelvin. So we mimic that type of core surface. Then we can introduce liquid ethane, gaseous ethane, and ethane at that temperature will liquefy. Once it liquefies, it will recreate the seas or the lakes on Titan. So we do have the, let's say, the template of the basic surface of Titan. And then what we can do is slowly introduce different molecules. For example, acetonitrate, propanitrile, which we studied in this presentation, which we'll present here. We would introduce them. Once they get in contact with ethane, their solubility is very low. So they will precipitate, and they will precipitate as solids. So if we do that precipitation in solid, we can in a way mimic what would have happened on Titan if we had that precipitation, of course, on Titan. Now, this capillary that I'm talking about would be subjected to probes. And those probes is how we learn about the processes that are going on Titan. In our case, we are, for example, subjecting it in a diffraction capillary, as I said, and we collect diffraction data. The diffraction data will be collected as these processes are going on. For example, we can even collect data while we are freezing the water, so we can learn even something about freezing of the water. But then we will collect data throughout the whole process. At the end, we will heat and cool just to mimic the precipitation and evaporation of the lakes. We can also slightly reduce the pressure to initiate a little bit more of precipitation, or dose a little bit more ethane or methane to initiate rain, and follow each of these processes by diffraction or by spectroscopy. By doing so, we can learn about the processes that are undergoing in this microenvironment, and possibly translate and learn something about the macro processes that are going on Titan. Now, we are well aware that this is not linear, and that we cannot guarantee that 100% we have the same conditions that are in Titan, but we are doing our best. And as I said, in the planetary research, when we try to understand a planetary body that is thousands and thousands and thousands of miles away from us, this type of precision is pretty much good, and also it's better than nothing. Currently, we know nothing about these processes, and it's better to know something, to start from something, and then to build on that. Now, as you mentioned, we do need collaborators. We cannot do this by ourselves in the lab, just because this type of solid-state organic research is complicated. So we do work with a couple of national centers in the United States. So we collect diffraction data and total scattering data at APS, Argonne National Lab, Advanced Photon Source. They have been extremely helpful in designing the cell and making this happen. Then we have an excellent collaboration with National Institute of Standards and Testing, NIST, with collecting neutron data and neutron spectroscopy. That is incredibly important, considering that Titan is organic. The surface in Titan is dominated by organic species, and as people might know, for detecting hydrogen atoms and hydrogen compounds, neutron diffraction is extremely important. Then we have, currently we started another collaboration with Oak Ridge National Lab, and as we speak right now, we are collecting neutron spectroscopy data that hopefully will inform us a little bit more about the destruction of Titan. We also have collaborations with several universities in the United States, with NASA, of course, with GPL, which have a group that is extremely prolific in this field. And we also use a lot of supercomputing capabilities, such as the mainframe supercomputer at SMU.
Great. Well, sort of to wrap up then, what would you like viewers to take away from your talk today?
Well, there are a couple of things that I would I would hope that the viewers will take away. The first is that Titan is the next frontier, and as you might know, NASA will send a mission to Titan in a couple of years. It's called Dragonfly, and the Dragonfly rover will spend a couple of months in Titan. That mission will descend in just a couple of years and is expected to arrive in Titan in a couple of decades, which is in our lifetime. So in our lifetime, we'll have experimental setup roaming on Titan for a couple of months, and that is quite interesting. So that would be, I do believe that it's very, very important right now, more organic chemists, physical chemists, to get included in this type of research, because let's say in 20 or 30 years from now, when the Dragonfly will touch down on Titan and start collecting data, we will need this type of models. We will need this type of libraries, spectroscopic libraries, thermodynamics libraries, and so on, in order to inform and to help this epochal NASA mission. Again, this is our next frontiers in space explorations. We'll learn so much more. We'll learn something about the next of kind to Earth, and I do believe that that's very important. Scientists from NASA also believe that there might be life on Titan, life that maybe definitely will not be the way we know it, but still it might be life. And in order to detect that life, in order to understand it, we do need these models. We do need to know a little bit more about how this surface would look like. Another thing that I would like the audience to take away is the fact that, and this is quite interesting, it absolutely does not apply only on Titan. We are working quite much in phase diagrams and crystal structures. In the 60s and in the 50s from the last century, the phase diagrams were studied so much. Crystallography was one of the most important techniques for science. As time went by, those techniques were either forgotten in the case of phase diagrams, or crystallography was quote unquote downgraded to merely just a characterization technique. But there is so much more to learn. For example, the fact that we don't know the phase diagram of acetonitrile and propionitrile, or previously published phase diagram of benzene and acetonitrile in the 21st century, that is quite surprising. Those are the chemicals that we need and we use every day. That is a fundamental knowledge. Similarly, not knowing the crystal structures, one of the most fundamental descriptors of the system in the 21st century of common solvents, it's something that I cannot wrap my mind on. And but I do believe that it will be quite beneficial if our generation of scientists really looks a little bit back in order to go in the future forward.
Well, great. Thank you. Media briefings for ACS Fall 2021 will be posted throughout the meeting at www.acs.org/ACS Fall 2021 briefings.